graphic studies in the structural analysis of R-type structures. And a bit beyond that, to preserve structures, and this is going to be, I guess, a relatively short presentation. We're going to go over principles mainly, first with an introduction. Just basically building upon what Alessandro just talked about. Graphical techniques are serve the purpose of analyzing forces in structures, and they've been around for a while. So actually the law of parallelograms was sort of proposed in the 16th century. Then in the 18th century, the funicular polygon was sort of proposed. And then relatively recently, in 1886, Kuhlmann published the first book on graphic analysis. It doesn't mean, however, that we didn't know about it. This is just the first formal publication on the subject. And then several contributions from Maxwell, Cremona, Moore, Ritter, and another Ritter between 1850 and 1910, mainly Germany and France. So we're going to basically introduce the concept of graphic statics. Let's say that we want to define what is a funicular. And if you think about it just in terms of geometry, it's the shape that the structure needs to adopt so all its members are in tension. Or we can say also compression, tension or compression, but it's basically a shape. That's what defines the funicular for a particular load. So let's say I have a cable and I hang this cable. For the sake of this conversation, I'm ignoring the self-weight of the cable. So this cable supports two loads, 4 tons and 10 tons. So I can find what would be the shape that this cable will take if we hang these two loads from it. That's what we call the funicular. Now, what is a force polygon? Now, if I take a closer look at what's happening at every single node, I can basically come up with what we call a equilibrium equation. And if I closely add forces here and add forces here, I'm going to get to force polygons. So the force polygon, in a way, it's the way that we verify that our funicular is valid, is what is going to happen. And from it, we can basically conclude that the cables are parallel to the forces. This force of 9.2 is parallel to this cable. This one is parallel to this other cable here. And this one being parallel to this cable here. Now, interestingly, if I think about the cable, right, and we hang the loads and we just flip it around, it's just multiplying everything, let's say, by -1. So rather than having a member in tension, what happens now is we have a member in compression. And this is what defines basically the shape of an arch. So let me give you an example of a masonry arch. And we're going to design, a relatively simple arch. And let's say that this is the arch that we want to define. This is a masonry arch. And this is the axis of the arch. And I'm going to start off with a first approximation to the geometry. And this is a lot of information here, but what I want you to keep in mind is that my first approximation is this triangle. It's not really complicated. It's very simple. This is my first approximation. Now, the next thing that I'm going to do is I'm going to calculate what are the loads that this member sort of supports. And that's basically the weight on top of it. Then that weight, I'm going to hang those weights from a chain. And this is what I'm doing here. I'm hanging the weights from the previous slide. I hang them here, and this is the shape that that chain will take. Now, we can go through methods, but this is basically educated guessing or rules. We're going to draw the force polygon or the for these forces here. And if I draw the force polygon, can give you some rules. We can basically come up with this set of forces here, which are the weights that we were hanging from this. And based on this shape, which has two characteristics, one that it is horizontal here, meaning that I want my arch to be horizontal here. And this inclination here, where we have the 48 tons, which is basically telling me that this is the inclination that I want for the springing of my arch, I can redraw my arch, and I will eventually, after a few iterations, I will come out with the black solid line that we see here. So we started off with the first approximation, we calculated the weights, we hang the weight from a change, we sort of flip it around, we calculate the weights again on top of that chain that represents the arch, and we continue to do the process, and it quickly converges to my arch. So it's a very powerful tool, and we know for sure that this is under full compression under these particular loads. And again, this is parallel to this one, and this is parallel to this one. So these little triangles here represents, if you will, the force equilibrium or the force polygon for each of the nodes of my arch. So it's a very powerful tool for sizing or getting the shape of a structure. And this is how it would look like. Let me show you an impressive example. This is the Strasbourg Cathedral in France. And this is the facade, but this is inside. So this is what this shows us is the thrust or compression thrust of this structure here. So we can design arches, but we can also come up with the shape of the structure in such a way that forces have or find the path to travel. So in this particular case, we're showing how the forces transfer from, let's say, the arches to the columns and so on, all the way to the floor. And in this particular sketch, we're also showing what would happen if we had wind load, transversely to our structure. And as long as this thrust falls within our structural elements, we are safe. Let me go into a bit of more in-depth or analysis of arches, and we're going to talk briefly about limit analysis of arches. And the basic theory is that if we are investigating the strength of an arch, this is basically the way that the arch will fail. So we may crack our arch, so to speak, or we may have a compression thrust that it's basically going around the edges of your arch, and that leads to compression on one end, but tension in the opposite end. Or we may have this other scenario, but in any case, these are the points that will probably lead to the collapse of our arch. So this is the first thing that we have to imagine. We have to think how our structure or our arch can collapse. And this is a landmark paper, if you're interested in this. This was published by the American Concrete Institute on how to investigate the strength of arches. So the idea is based on what we call a collapse mechanism. So let's say we have an arch, and this is how we envision that this arch is going to fail, right? And if we know or we anticipate how this is going to fail, we can come up with what we call the instantaneous center of rotation, and from it we can see how it will basically slowly collapse, and we introduce what we call a virtual rotation. So we have a way of anticipating how the structure can collapse, and this is basically based on your intuition that you can come up with this. This is from that paper, but basically this explains a lot. So what we are doing here is we're going to calculate, let's say how much load can I apply before it fails. That's what we want to calculate here. So this is the P-safe. So we are going to assume a collapse mechanism, which is what we just did, envision how this can collapse. And then once we have that deflected shape, we calculate a quantity that we like to work to call virtual work, which was proposed centuries ago, which is basically the product of the force times the displacement. And that displacement is when the arch is about to collapse. This is just an exercise that we're doing. So by doing so, let's say this load P will have to undergo this much displacement here. But to do so, because the arch is so heavy, this section of the arch here wants to push upward. but you have so much weight on top of it that the amount of work that it takes for that weight to do that work is huge. And as a result, when you do the calculations and you formulate your equation, you solve for P, you conclude that typically the collapse load for these arches is it's order of magnitude higher than the loads that they see. In other words, they are very heavy, and to make them fail or to make that compression thrust go out of the arch takes a lot of load, and that's why we see these resilient structures, thousands of years still there. We have to do this, however, for several mechanisms, and then we pick the minimum P, and that gives you the collapse load. Another interesting method is the finite element analysis of arches, and you're going to find plenty of literature on this topic. So this is an arch in Anatolia in Turkey. This was built in 1460, so pretty resilient structure, I would say. The arch is 4.7 meters wide and has a span of 8 meters. And the thickness is 0.45 meters. And we can come up with a SAP model. SAP is just a software to do finite element, as we're showing here. And you can get very impressive results, by the way. You can get stresses, you can get forces, you can get displacement. So this is a different resolution, so to speak, if we compare with what we can get from our graphic statics or linear analysis. However, there is a caveat that I want to share with you, which is that finite element models, they're very powerful, but they're not good at representing cracks or mortar behavior. So the moment that you get a crack, everything changes in this model, and that makes difficult to fully rely on the calculation. So in my opinion, these are great tools. They show you contours and they're very appealing, so to speak, but unless you can verify this with graphic studies or limit analysis, just be careful with the interpretation of results here. And just to close, I'm going to talk a bit about the preservation and retrofitting of arches. Again, another paper to give you some insight published by the American Concrete Institute on analysis of techniques to strengthen arches. And we're going to talk about this Castel San Pietro in Verona, Italy. This castle you can see here is at the top of this hill. And what is interesting about this is that it had a vault which was scheduled for demolition. So this was a great opportunity to test this vault prior to the demolition. So what they did is they cut the vault in 3 segments, and they strengthened 4 segments, actually. They strengthened 4 of them, and the 3 of them, and the 4th one is just the unreinforced. So is your baseline comparison. So one of the segment was strengthened with carbon fibers, which is pretty popular nowadays, and was glued with an epoxy resin. The other one was strengthened with a steel reinforced grout. And the third one was strengthened with basalt textile reinforced mortar. And this reinforcement is applied to the top of the board, right? Just for clarification. This is how they tested this. So basically, you see the vaults here, 1, 2, the arches, I shall say now. Now, we are loading these downwards similarly with the example that I show you with limit analysis, and this is how they do it. They have some hydraulic jacks and a beam, and they push downwards until you fail the arch. And then we can monitor basically 2 things. We're going to monitor how much force we apply and how much displacement are we measuring. And when we look at this, this is the way that they strengthen the arches, right? We have, the FRP to the left. Then we have the steel reinforced grout, and then we have the basalt textile to the right. And I'm showing you here the failure modes after you apply that load and it fails. Now I'm going to show you the results. So what we have here is on the y-axis we have how much load we apply to the arches, right? How much was applied with the jacks, and the horizontal axis is how much displacement are we measuring. The first line here is the black one, is the unreinforced arch, right? So we didn't do anything. By the way, they don't have much load on top of them, so it fell relatively quickly. Then we have the carbon fiber reinforcement, which is shown here in blue. And two things, I mean, note the gain in strength, but not only gain in strength, also gain in deformation capacity, right? So it can deform substantially prior to collapse. The red one is the steel reinforced grout. And again, we note a similar trend, not only a gain in strength, but also gain in deformation capacity. And this fourth one or third reinforcement technique, which is the basalt textile reinforced mortar, you can see here is the orange one. And this orange one is giving you plenty of strength. This one here, not this one here, but very little deformation capacity, right? This one here. So, I mean, the conclusion is apparently from this experimental study, FRP, which is very popular and is relatively inexpensive, by the way, is a good way of strengthening arches if you need to do so, particularly for preservation purposes. And also the steel reinforced grout is a good technique for this purpose. Let's go to the conclusions. So keep in mind that graphic studies is probably the most versatile and easy to use method for analyzing and designing R-type structures. Limit analysis is easy to use and is very powerful for determining the strength of arches. It gives you the exact solution, by the way. Finite element, I mean, it's a powerful tool, no doubt about it. Interpretation of results, however, is challenging. And keep in mind, it can't reproduce cracks, and that's a huge shortcoming, or can't represent cracks reliably. To strengthen and preserve arches, the use of steel reinforced grout and carbon fiber has proven to be a successful technique. So when you face similar situations, you know where to look for. And resources, National Park Service, American Concrete Institute has plenty of information on retrofitting any type of structures. The Earthquake Engineering Research Institute, if you end up dealing with seismic or arches or historic structures in seismic regions, is a good resource as well.